Okay, we're gonna start the water section, and it gets into a bit of the osmotic balance bit. So we're gonna go through a few slides and kind of outline that, and then we're gonna jump to another video that I think does a really good job of explaining some of the complexities around it, and then come back and kind of break that down. So right now for this video, we're just trying to get to some terms and some concepts, and then we'll apply it. So water is the medium in which all biochemical reactions necessary for life occur. Water is life. Its unique properties make it a universal solvent for biologically important solutes, and organisms must balance uptake with loss of water and solutes, primarily salts. The movement of water and salts influence each other. Now, the book uses a few terms, and I want to kind of give some examples of those terms in context here. The book uses the terms isoosmotic, hypoosmotic, and hyperosmotic, and it's referencing the organism compared to. It's referencing the environment compared to the organism. So you can use these terms either comparing the organism to the environment or comparing the environment to the organism. So if you're looking up for in-depth information about any of these terms, make sure you're referencing, in this context, these terms are referencing the environment compared to the organism, because all of these terms are comparing this to that. And if you compare organism to environment or environment to organism. So if we kind of go down and you can use these terms in either direction is what I'm trying to say. And the way that I want to use them is to reinforce the way that the book is using them, which is comparison to the environment. So isoosmotic is the same salinity in the environment as the cells. Don't have an image of a cell here. This is in fact an image of a fish. And here the salts and water diffuse at equal rates in and out of the organism. So the concentration of salts within the organism is the same as that of the environment. Similar to what we see in many marine organisms, where the salt concentration within their body is in equilibrium with that of the environment. They are isoosmotic. Then you can have hypoosmotic. Hypo, less. We're talking, now what are we talking about when we say hypo? Again, we're talking about the environment. So the environment is less saline than the organism's cells. An example of that could be if you take a marine fish and you throw it in fresh water. That marine fish, the cells within it are in equilibrium with the marine environment. So we know that they have a fair amount of salt in them. Now you put them in an environment that's less saline, freshwater, what happens? Salts will diffuse out at a higher rate while water diffuses in at a higher rate. So in this image here, you can see salts are darker, so salts are going out, and water's darker, water is going in a hypoosmotic environment. Then we can have hyperosmotic, hyper, more. We're talking about the environment. So the environment is more saline than the organism's cells. I'll move me here. So in this example, the environment is more saline than the organism's cells. So now we're going to go take a freshwater fish, we'll go catch a walleye, and throw it in Puget Sound. The environment is saltier than the cells within that freshwater fish. So what's going to happen there? Salts will diffuse in at a high rate while water diffuses out. So if an organism is in a hyperosmotic, I keep saying osmotic, a hyperosmotic environment, then salts diffuse in and water goes out. Shrivels up and dies. In this instance, water's leaving, salts are coming in. In a hypoosmotic environment, where we take our saltwater fish and throw it in a pond where the environment's less saline than the organism, water goes in, fish explodes, salts go out. So when we use these terms, they're intuitive, but we need to reference we need to make clear what we're referencing. So hypo, less osmotic, environment. So we're using all these terms in relationship to the environment. Now, water flows down along energy gradients. My father's a plumber, and every plumber I've met generally knows the 3 rules of plumbing. Payday's on Friday, don't bite your fingernails, and blank rolls downhill. Gravity, water flows downhill following the gradient of potential energy, intuitive. It's the gravitational potential. And pressure, water flows from an area of high pressure to lower pressure or Tagore potential. Now, when we get into pressure, it gets a bit stickier, and so that's kind of where we'll slow down and think about what we mean by types of pressure. A few terms we need to think about is osmotic potential. Water flows from a region of high concentration to a region of low concentration. And it's a bit, to me, counterintuitive. So when we say high concentration, we actually need a higher concentration of water. So a low solute concentration to a region of low concentration, also known as a region of high solute concentration. There's a video in a minute that will help explain that. But one way of thinking about that is if we've got salt water and fresh water, per this definition, fresh water is high concentration and salt water is low concentration, because salt water has a higher solute concentration and fresh water has a lower solute concentration. So it's a bit counterintuitive, but that's what it's stating. Now, the matrix potential is the energy associated with attractive forces on the surface of large molecules inside cells or on the surfaces of soil particles. This is frequently discussed as it relates to soils. And similarly to what we talked about earlier with volume to surface area, if you have a lot of fine sediments, there's more surface area and the water is going to be more sticky. It's attracted to the surface of those soil molecules and particles. Where if you have larger grain sediment, gravel, sand, etc., water is going to flow more freely through that because there's less surface area for it to stick to. So here's a cross-sectional diagram of soil showing a variety of particles. And you can see here where water is like adhering to the particles and creates a film around those particles. So if you have smaller particles, you have more surface area per volume. So if you have a beaker of gravel, think about the amount of surface area in that versus a beaker of really fine soil. You're going to have more surface area in that finer soil, which is going to cause more surface tension and the water to cling to those soil particles more strongly. That's our matrix potential. And it's dependent on the soil type. Not all soils behave the same way. And so that's generally a way of thinking about matrix potential. And we'll talk about that when we talk about water movement and absorption into plants from soil. Now the next bit is talking about water potential with a kind of scary looking equation. My recommendation is to stop and watch this video linked here. It's a bit more chemistry than we need, but it shows very clearly the factors that are important to water potential, and I think that's going to help us. In the video, they use the term solute potential. In the parlance of ecology in this book, that pretty much equals osmotic potential. So when they talk about solute potential, just insert osmotic potential in your mind. It's a quick 5-6 minute video. So we're going to pause here, watch the video, and then we'll come back and break down the factors that are important to water potential, and then look at that in relationship to how water moves through plants. Okay, so take a look at that and come right back.